Welcome, everybody. I see some familiar faces who were at yesterday's talk. This is a first. We've never had two math seminars back to back, and to have them both with my students is extraordinary. It's our pleasure today to welcome Stephen Janke, who is taking our History of Mathematics seminar this semester. We offer it every couple of years. Early on, in fact, I think it was actually before the seminar even started, you'd said you were kind of interested in hyperbolic geometry. Mm-hmm. Well, one thing led to another, and one day I said, so does anybody plan to present their project for the history seminar as part of this seminar series? And he said yes. So here we are. So, all right. They didn't even do anything yet, they're clapping.
All right.
If you need anything, let me know.
All right.
I'll be here.
Well, when you're going to talk about geometry, it's really only fair to start off with Euclid. And what Euclid did is he wrote a book called The Elements. And in it, it contains several propositions about geometry, several useful results that you could use in it. And when he started off with 5 axioms, 5 postulates, 5 things he assumed to be true. And a couple of them are pretty obvious. And one of them, the first one is that if you're given any 2 points, there is a line connecting those 2 points. The second one is that if you have a segment like this, you can extend it indefinitely. The third one is you have a point and you have a distance. You can construct a circle of that radius around that center, around that point. The fourth one is that all right angles are the same in the sense that all right angles are congruent. All right angles are 90 degrees. And then the fifth one is really where some problems started to happen. I'm going to try and say this as Euclid did. If you have a line that falls on 2 straight lines, and the sum of those interior angles add up to be less than 180 degrees, then those 2 lines, if produced indefinitely, will eventually meet. It's kind of different than these 4 over here. And there's an easier way of saying that. It's called Playfair's axiom. That is, if you have a line and a point not on the line, there's exactly one line through this point that is parallel to this line. And it's the same thing as Euclid's 5th axiom, the parallel postulate. So we get to work with this instead. Now, one of the things that was a problem was that Euclid's 5th axiom, it did stand out as different than the rest of them. It was definitely more wordy, it was definitely longer, and it wasn't as obviously true. I mean, with these ones you looked at and you go, well, sure, yeah, they're true. The 5th one, you kind of had to think about it for about a couple seconds, and then you go, sure, why not? So instead of just continuing on and assuming it's true, mathematicians tried to prove Euclid's 5th postulate. They tried to deduce it using his first 4. And most notably out of that is the work of Saccheri. And Saccheri wanted to prove Euclid's 5th postulate, again using the first 4, in something we now call absolute geometry. And that is a geometry where you assume Euclid's first 4 postulates are true. And Saccheri's work, he started off with the work of his quadrilaterals, and that is, you're given 2 lines of the same length, A, it's a B, C and D, and they have a base here. And then it's this last side that was really important to Saccheri's work. He considered there are 3 different cases to consider. One was if Euclid's was true, if Euclid's postulate was true, then these angles at A and C are 90 degrees. Then the other 2 cases were this angle is greater than 90 degrees, or this angle is less than 90 degrees. And what Saccheri was able to show was that there is a contradiction if you consider a case where this angle is greater than 90 degrees. And that's something that's now known as the Saccheri-Legendre theorem. We're going to walk through a proof of that real quick. But first we're going to need to prove a lemma that's going to be useful in that proof. And that lemma is that if you're given any triangle A, B, and C, it is possible to construct another triangle A1, B1, and C1 such that their angle sums are the same and that the angle A in the first triangle is always going to be greater than, that the angle A1 is always going to be less than half or equal to the angle of A1, the angle of A, And we start off the proof of this lemma. We start off with a triangle. And we start off triangle A, B, and C. And what we want to do is we want to construct triangle which satisfies these two things. So what we do is we make another line, and we make it so that it goes through the midpoint of B and C. Another thing we do is we make sure that this segment here, I'm going to call this D, this segment is equal to that segment. And we're going to call this E. Now we know that this segment and this segment are equal, and this are equal. So BD and DC and AD and DE are equal. We also know that these two angles are equal. That's something that Euclid showed, but when Euclid showed it, he didn't use his parallel postulate. So it's a perfectly good proposition we can use in absolute geometry. You don't need to worry about whether or not it's true. So we know that triangles A, D, and B, and DC and E are congruent. One of the things I'm going to do here is I'm going to go through, I'm going to label a couple of these angles here. So one of the things we now know is that angle 4 is equal to angle 5. We also know that angle 3 is equal to angle 6. So now we're going to sum up these. We're going to sum up the angles of A, D, and B. I'm sorry, not A, D, and B. A, B, and C, and A, C, and E. So we're going to get okay. So now that we've done this, we can show that, because of these substitutions, that these are equal. You know, we can plug in 4 for 5 and 3 for 6, and we still get angle of 1, 2, 3 plus is equal to the angle of 1, 2, and 3, and 4. So we now show that these are the same angle sums. So we have one of these done. So now we need to do this one. And you'll notice that the angle 2 is in AC and E, and angle 3, so these two have to sum up to equal this one. So we know that angle 2 plus angle 3 have to equal the angle A. Now we know that one of these has to be less than or equal to half the angle of A, because if both of them were, then this sum would be bigger than that angle. So these two together is not angle A. That's not true. Kind of see that. So one of these has to be less than or equal to half the angle of A. And we're just going to say that angle 2 is that angle. So we now have that. Which means we now know, we have shown that it is possible to construct a triangle of A1, B1, and C1 such that their angle sums are the same and that the angle A1 is less than or equal to half the angle at A. And this gets pretty useful when we're going to show the Sakari Legendre, let's see how I spell that. Theorem. Now, this theorem states that the angle sum of any triangle A, B, and C is always going to be less than or equal to 180 degrees. Any triangle. To start off this proof, we're going to do something Sakari did for his proofs, is that we're going to assume the opposite of what we're trying to prove. We're going to prove this by contradiction. So we're going to suppose not that the angle sum of triangle A, B, and C is greater than 180 degrees. And we can say that a little bit differently. We can say that the angle sum A, B, and C is actually equal to 180 degrees plus alpha, where alpha is some positive degree angle. So we start off with the triangle with that angle sum. So we start off with this. But from over here, we know that it's possible to construct an angle with the exact same angle sum, and that the new angle A from that triangle is going to be less than or equal to half the angle of this original one. So we're going to get the angle sum of A1, B1, and C1 is equal to 180 degrees plus alpha. But we also know that the angle A1 is less than or equal to half the angle of A. But why stop there? We can apply this as many times as we want to, and if we apply it again to A1, B1, and C1, we're going to get A2, B2, and C2 with the same thing true, except this is now 2 and that's 1. We can apply that as many times as we want, and what we end up with at that point is we still have the same angle sum. But here we have the angle of AN is less than or equal to 1 over 2 to the n, the angle A. Now this is pretty important because we can take this as many times as we want to, and if we take n to be big enough such that this new angle is less than alpha, we can actually get some useful results from that, and that is we have 180 degrees plus alpha, so the original angle sum, that is equal to the angle of AN is the angle of BN plus the angle of CN. And we know that this is less than alpha plus the angle of BN plus the angle of CN. So if we take this one and this one, and we subtract alpha from both of them, we get 180 degrees is less than the angle of BN plus the angle of CN. This is saying that two angles in a triangle, when you add them up, it's greater than 180 degrees. And again, we know that this is false. This is a contradiction to Euclid 1, proposition 17. And that is another proposition of Euclid that is true in absolute geometry. And because of this contradiction, we can now show what we were originally meant to show, that the angle sum of any triangle, A, B, and C, is always less than or equal to 180 degrees. Now, this was a big deal for Saccheri because he set out originally to prove Euclid's parallel postulate. Instead, he's shown that there is now another case that is, I guess you could consider, equally valid as Euclid. Instead of proving the Euclidean case, he has now shown that it's now in even more peril. It's now in more danger of being wrong. But to continue this story, we're going to need to go to Hungary and Russia, the two mathematicians from both those places, John Bolyai and Nikolai Ivanovich Lobachevsky. And a little bit of background on these two is John Bolyai was a Hungarian mathematician. He was the son of Wolfgang Bolyai, who studied at Göttingen, and when he was there, he became a close friend of Carl Friedrich Gauss. And Wolfgang Bolyai was a famous geometer. He worked in geometry, and his son, John Bolyai, learned about the problem of parallels from him. So when John Bolyai found out about the problem, he also sent out to return geometry back to its pure Euclidean roots. And he didn't quite do so. In fact, he changed his mind. Instead, he found a new geometry that was logically consistent as Euclidean geometry, but also he found a new word. He created a new word out of nothing, and that was something John Bolyai wrote in a letter to his father, saying, out of nothing I've created a new word, and all else I've sent you before is like a house of cards compared to a tower. Lobachevsky was a professor at Kazan University in Russia, and in 1826 he gave a lecture on this new thing that he found, hyperbolic geometry, in which that, in the word of Playfair's axiom, you had more than one line through that point that was parallel to the initial line. And in his attempt to publish some of his works, the St. Petersburg Academy of Sciences didn't publish his work too much because they thought it wasn't precise enough to publish under the auspices of the Academy. So when we're really talking about the work of Lobachevsky and Bolyai, it's convenient to look at them at the same time because their work is so similar. So we now have the new case. We now have a line and a point not on that line. But instead, we now have a new postulate to use, a new parallel postulate, the Lobachevskian parallel postulate. And that is, given a line and a point not on that line, there are two kinds of lines through that point. You have cutting and non-cutting. And a non-cutting line just doesn't cut this line into two pieces, and the cutting line does. And he said that the boundary between those two classes are parallel. So we have a new line, comes through this point, goes off here, and it observes asymptotic behavior to this initial line. This is parallel to this. But more than that, you can do that from both sides. You have another line over here that observes asymptotic behavior over here, and you now have more than one line through that point that's parallel to the initial line. And in this new geometry, this distance right here, this perpendicular distance, which we'll call P, is pretty important because this angle, and this was the work of Lobachevsky and Boya, they showed that this angle right here, which is called the angle of parallelism, denoted by this, is dependent on this distance here. And they found a formula that you can use to calculate this, and that is 2 times arctangent of e to the negative p, where p is this distance from the point down to the line. And you can use that to find the angle of parallelism, and for the line coming from over here, that angle of parallelism just also happens to be the exact same. And in continuing with this work, Lobachevsky and Boya, they discovered a new curve with an interesting property. It's called a Horus cycle. That's that. And if you have an initial line make an arc of a circle here, get a pretty good approximation for the Horus cycle. If you take a line like this that is perpendicular here, it also just happens to be an asymptotic parallel to this initial line here. I'm going to call this A, call this E. More than that, you got another line up here call this C and call this B. You had the same thing up here. And again, if we want to use this formula again, we just take the distance from B to C, we half it. And then we can plug into this formula and we can find out the angle of parallelism. Now this is all pretty cool, but we need a better picture of what on earth is going on in the in the hyperbolic plane. We need a better model of it. And that's where the work of Felix Klein and Henry Poincaré comes in. And the Klein-Beltrami model is a circle. And the circle is special in the sense that it is infinite in its radius. So if you have a circle here, centered there, each point on this circle is an infinite distance away from this. It's infinitely far away. And we called the points on the circle ideal points, or points at infinity, or omega points. They're all names just to describe. It's a point on the circle. And the point on the circle isn't in the model. In fact, everything outside of the circle isn't in the model. This entire model represents the entire hyperbolic plane. So if we have a line here, you have another line here, it's pretty obvious to go, yeah, they're going to intersect, and they're going to intersect somewhere around there. But that's outside of our model, which means that point is not in the hyperbolic plane, which means in the hyperbolic plane, these two lines are parallel to each other. So if that's parallel, what's perpendicular? So if we're given another line here, now to find perpendicular lines to here, we're going to need the pole of this line. And how to get the pole is a simple matter of making some tangents to the circle at the points where that line intersects the circle. And this is the pole. This is the pole of L, and you can also call L the polar of P. Now, any line you can draw in the model that if you extend outside the model to go through this point, it is perpendicular to this line. So if I draw this, this angle right here is 90 degrees, although it doesn't seem to look like it. So in this model, our sense of angles, we don't really have that. But we still have our sense of straightness, though. And to correct what we want to get a good idea, a good look at this angle, we need another model. We need the Poincare disk model. And in this model, we still have the same thing. We still have a circle. And the points on the circle are still ideal points. But now we have to make lines a bit differently. In fact, lines are actually arcs of circles as well. Centered there. Now, lines may be arcs of circles, but there's still a couple special lines in here that are still straight, and those are the diameters. The diameters of this circle are always going to be straight, how we think of them. But other lines, say a line through here, how to make a line through that ideal point is you make a tangent. Then you pick really any distance away from here, and that will be the center of your new circle that you can use to draw a line in this new model. And because of the construction of the circle, we also know that this and this are right angles. It intersects the outer circle at 90 degrees. And we can make different circles of different lengths by simply changing the size of the circle we're drawing. So that's how you can draw lines from two ideal points, but there's still a way to draw a line, say from an ideal point to a not ideal point, to a point somewhere in here. And let's say I want a line from this point to here. Now, how you do that is you simply make a straight line, a different color, through these points. And you want the Euclidean perpendicular bisector for this line. So we're just going to make that real quick. And I'm only going to draw one of these, though. So now we have this, and this is the Euclidean perpendicular bisector for this red line. Now, it's this intersection that's important. This is, we all know, well, now that we now know, any line in the hyperbolic plane that goes through this point has a center on this line, and we now have our new center of that circle. Take this. Okay. So there's that. We now have a line from this point to a not ideal point. And there is a way to construct a line from two not ideal points. And simply to do that, you make a line, and you make the line from each of those points to the center, and you make a perpendicular that you take their intersections, take the tangents. The point of that is now going to be another point on the circle you use to connect those lines. But it's a bit of a lengthy procedure, so we're not really going to do it here. And one thing we will do, however, is we're going to now connect these two lines, and we're going to see a hyperbolic triangle. So we do the same thing, connect these 2 points. Seem to be having trouble here. I think I may have drawn it wrong. Seems I have a bit of a problem. But yeah, you're going to get another arc. Oh, right. I know what my problem is. I've been trying to use this tangent line. I need this tangent line. There we go. So now we make the perpendicular. Construct its bisector. there. And there we go, there's our new arc of this circle. And it connects all these points. And as you can see, if you look at these angles inside the triangle, if you add them all up, you're going to get something less than 180 degrees. And that's how you construct a hyperbolic triangle of two ideal points. So this is an ideal triangle. And if you have any shape in here of the same thing, if you have an ideal point in the construction of that shape, it's going to be called that ideal shape. So if you have a perpendicular in here and it has a point on that, you're going to get an ideal perpendicular. And you can actually make some really cool tessellations in this, where you deal with other arcs of circles and you make tessellations of different shapes in there. So we covered the models, we covered some of the background of this geometry. So on what kind of surfaces, if you can use Euclidean geometry on any flat surface on any plane, what kind of surfaces does this geometry happen to appear, does happen to show up? And it was actually a combination of Riemann and Gauss who did that. Riemann said you could do any geometry, you can do geometry on any surface, but you have to change your axioms a little bit. Instead of just having a line connecting those, you have any generalized surface, your new line is going to be the line of shortest distance between those 2 points. And Gauss said that if you have a generalized surface, you know which geometry you're going to use by looking at what we call the Gaussian curvature, the product of its two principal curvatures. And for easy shapes, you can find the actual Gaussian curvature for quadric surfaces anyway, as far as easy surfaces go. You can find the Gaussian curvature by parameterizing the surface and plugging into a formula. But for a generalized surface, you're going to need to find its principal curvatures are the eigenvalue of its shape operator. And to do that, you're going to need to know a little bit about differential geometry, and we're not going to cover that. So if you're really dealing with a general surface, there is work done by 2 people at the University College of London, and we know how to find the Gaussian curvature of a quadric surface. We parameterize it and we plug into the formulas. And what they did is they can actually make a good approximation of the Gaussian curvature for a generalized surface by using quadric surface patches. So they fit a quadric surface onto like a pear shape. And then they can use that to approximate its Gaussian curvature. That Gaussian curvature is going to tell you what kind of geometry you're in, whether you're using Euclidean geometry, hyperbolic geometry, or spherical geometry. Yeah, that's how some stuff about hyperbolic geometry.
Does anyone have any questions?
I'm always fascinated at that time frame when folks were doing this. Do you have any insight on how they were constructing these ideas? Obviously, they weren't using markers on the
Yeah.
board. So, there's history that Euclid was using sand and a stick, like some of these other mathematicians were talking about. Do you have any idea what they were actually using?
As far as Lobachevsky and Boya go, they're probably using ink and paper still. Lobachevsky was a professor at Kazan University, so he definitely had the resources to do some of that. Boya, I don't know for sure about. And same thing goes with Sakari and his work. I'm not sure exactly what he'd used to actually do this, but I'd imagine it's something very similar.
That's a difficult thing to think about. They didn't have nice things to work with. Like
Yeah.
Absolutely.
Okay, so the models, the Poincare model, the Klein Beltrami model, where you can actually, on a flat surface, you can pick these things. Did you get a chance to look at all into the use of those models in terms of whether or not, that there were really issues with hyperbolic geometry from the beginning as being taken seriously. Did you come across any discussion about how those models are used to show that hyperbolic geometry is as good as consistent as Euclidean geometry?
As far as in-depth discussion, no. I have come across several sources that state that they used the Poincare disk model as a method of showing it is as logically consistent as Euclidean geometry, in the sense of if you're in the Poincare model, so you have the circle, if you're in the center of it, everything is fine, but as you start stepping away from it, if you're a person and you're in the center, you start stepping away, you start to get smaller and smaller and smaller and smaller and smaller, and if you do get to the edge of the circle, you're now infinitely small.
Infinitely far away.
Only in my dreams.
Or if you're a physicist.
I resemble that.
Hi, Tom.
I resemble that.
Oh, really? Well, did you mention positive, negative, and zero curvature?
Negative curvature, it's really the sign of the Gaussian curvature. If you have a negative Gaussian curvature, you're in hyperbolic geometry. If you're in positive Gaussian curvature, you're in spherical geometry or elliptic geometry. And if you have you have zero Gaussian curvature, then you're in Euclidean geometry. You're just on a plane.
You mentioned that it wasn't publishable, or it wasn't published because they didn't believe it was precise.
Yeah, with Lobachevsky, he wanted to publish his work with hyperbolic geometry, but it was St. Petersburg Academy of the Sciences. Now, Euclid was truth for 2,000 years. You don't question Euclid, and Lobachevsky was questioning Euclid. He's taken one of the things Euclid assumed was true, and he kind of threw it out the window and started working new. And not a lot of people kind of liked that. So there might have been some of that in play, but the official reasons why Lobachevsky's work wasn't published was that it was not precise enough for the St. Petersburg Academy of the Sciences to publish.
Practically, what would that have meant?
Practically, it probably meant that he really didn't have enough useful propositions to use as far as like the equivalent of Euclid's Elements. It's a book full of propositions, full of useful results you can get from his 5 axioms. Lobachevsky probably didn't have that, and because of his almost heretical sense of, no, Euclid, what he was doing wasn't necessarily true, would have played a personal effect on what they would use as an opinion of his work.
Thank you.
I'm wondering if there was any impact with religious authorities when this alternative geometry was proposed, like Copernicus, or, were you aware in your studies where there was sort of
I don't think there was
negative
too much of a religious implication. As far as John Boyard goes, he published his work as an addendum to his father's work, and most of the mathematicians thought it was one of the most beautiful 20-page essays they've ever read. And some other ones didn't really like it because, again, we're talking about dismantling Euclid's truth, and a lot of people didn't like that. And it's the same thing with Lobachevsky. His work really wasn't published, again, for the same reasons as before. They didn't think it was good enough to publish under the name of the Academy of St. Petersburg. So as far as religious impacts goes, I don't know, but I don't think so. Anything else?
It was not met with a lot of positive. Mathematicians didn't think much of it first, but eventually it did find use. Get a chance to look into
Some of the uses of hyperbolic geometry.
applications of it and in the physical world applications of this.
Not too specifically. I know that it was Einstein who said that some of his theory of relativities would be more, I guess, more correct, if you want to put it that way, would be more correct in hyperbolic space and hyperbolic geometry rather than our standard Euclidean geometry. So there's that. You got Einstein with it saying, yeah, it's got some uses.
Space is negative.
Is there anything else?
I will thank you again. Mr. Jank, you'll have to hang around if you have other questions. We have lots of cookies like we usually do, lots of our next talk will be in September, and our speaker is none other than the eminent Mr. Lee. Yes. I actually believe you mentioned that that's when you wanted to give your talk, so it's official. Do you have any idea what the topic is, or?
Topic? We're going to talk about graph theory, obviously.
Really? I wouldn't have guessed. Okay, good. Do you have anything more than that, or is that all you're going to say? You're going to tease us? Just say graph theory?
Graph theory, yeah, it's vertex labeling and edge labeling.
Edge? Oh, okay. Good. Yeah, we're done for this year, but I think we have your plan.
He hasn't completely agreed to that. He said, I haven't.
He's looking really surprised at everything we're saying. So I'm thinking,
Am I involved?
Yeah, well.
Oh, okay.
there's going to be a talk in September, at least one of these two presenting. That much I think we can say. And we've got a few others lined up. I think we still have 1 or 2 empty spots available, Tom. So thank you all for coming. We really, really appreciate you turning out. And thanks again.
Yep.
Good job. Good job.